In this video, we're going to cover the law of sines. So previously, we've dealt with solving right triangles. Solving a right triangle means we come up with all three side lengths of the right triangle and all three angles of the right triangle. And the tools we used when solving the right triangles were SOHCAHTOA, that is, the sine is equal to the opposite over the hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. The Pythagorean theorem, the fact that angles of a triangle add up to 180 degrees, and calculations with trig functions. When we're dealing with SOHCAHTOA, we want to be able to calculate sine and the inverse of sine. So those trig function calculations when I'm dealing with things like SOHCAHTOA. Well, SOHCAHTOA and the Pythagorean theorem only work with right triangles. Therefore, we have to develop some other tools to solve non-right triangles. Now, when we're dealing with non-right triangles, the convention of labels is the following. We're going to have side lengths of A, B, and C, and angles of alpha, beta, and gamma. The side A is going to be opposite alpha. The side B is going to be opposite of beta. And the side C is going to be opposite gamma. So opposite angle gamma. That is going to be the labeling convention no matter what the shape of the triangle is. So in these two triangles, the one on the right looks acute, the one on the left looks obtuse with obtuse angle at beta, but we keep that same labeling convention. Well, here's what the law of sines says. For any triangle with the labeling conventions that we just discussed, the ratio of sine of alpha over A is going to be the same ratio as sine of beta divided by B. And that is also going to be the same ratio of sine of gamma divided by C. So in essence, what we're talking about is the ratio of sine of this angle with the length of the side opposite that angle. And it should make sense as these angles get bigger, the value, as the angles get bigger, the value of the side opposite should get bigger. So wider angles are going to have longer sides opposite of them. I'm not going to prove the law of sines in this video, but there will be another video linked in the playlist or linked in the description of this video, which shows you why the law of sines actually works. This video is going to be concerned with using the law of sines. So that's what we're going to do. We're going to solve triangles that are non-right triangles or right triangles using the three tools that we now have. We know that the angles of a triangle have to add up to 180 degrees. We know how to calculate with trig functions and their inverses. And now we have the tool of the law of sines. And many triangles can be solved using these three tools. So let's do an example. Let's say I have a triangle with this labeling convention. This triangle picture, by the way, is not to scale. It's just there for the referencing of the convention of how angles and side lengths are labeled. So as you can see in this picture, the angle alpha is not looking like it's 112 degrees. This angle looks like an acute angle, whereas alpha is actually obtuse. So let's solve this triangle. Again, using this information, the picture is not accurate to the angle and the side lengths, the angles and the side lengths that we're going to get. So we have this information. We have three pieces of information. One is that the side A is length 36.1. The other piece of information is that alpha is equal to 112 degrees. And the third piece of information is that beta is equal to 14 degrees. Now I'm going to lay out my answers like this. Alpha is 112 degrees, A is 36.1, beta is 14 degrees, B is unknown, gamma is unknown right now, and C is unknown. So in order to solve this triangle, I have to find B, gamma, and C. It doesn't matter what order I do that in exactly, but there is a convention that I always do. Whenever I have two angles, I usually find the third immediately. And what I'm using there to find the third is the fact that the three angles of a triangle add up to 180 degrees. So if I know that alpha is equal to 112 and beta is equal to 14, I can easily find gamma using this equation. Just take 180 minus 112 minus 14, and we see that gamma is equal to 54 degrees. So that's what I usually do first if I am given two angles. I find the third. Anytime I know two angles, I go ahead and find the third using the fact that the angles add up to 180 degrees. Now I'm going to focus on finding B, and then I'll focus on finding C next. So let's find B right now. Well, the law of sines says this: sine of alpha over A is equal to sine of beta over B is equal to sine of gamma over C. I know alpha and A, so I have one of the ratios. Beta I also have. So if I ignore this last equal to, I can use this ratio in order to solve for B. In other words, we're going to take sine of 112 degrees divided by 36.1 and set that equal to sine of 14 degrees divided by B. What you would do to solve this is you would cross multiply. That would give you B times the sine of 112 is equal to 36.1 times the sine of 14. And then you divide both sides by the sine of 112. So I'm going to do that all in one step. And it gives you a B value of this. Now, this is going to be the exact value of B. If I wanted an approximate value, I could just round that answer to 2 decimal places, and that gives me a B value of 9.42. So I'd go up here and say my B value is 9.42. And The last unknown to find is now C. Now, because we have a B value, if I wanted to, I could use this ratio in order to find C. I know the beta now, I know B value, or at least I know approximate B value, and that could be used to find the C. However, what I usually do is I use this ratio because my A was given to me as the exact value of 36.1, where this B was actually a rounded value. So I utilize the exact values when I can. In this case, I'll use sine of alpha over A is equal to sine of gamma over C. So in our case, sine of 112 divided by 36.1 is equal to sine of 54 divided by C. Again, I'm getting 54 because we earlier found that gamma had to be 54 degrees. You're going to solve this just like before. We're going to cross multiply. That's going to give me C times sine of 112 is equal to 36.1 times the sine of 54. And then we're going to divide both sides by the sine of 112. Once again, that's the exact value of C. If you want an approximate value of C, that would be 31.50. That is rounded to 2 decimal places. One little note, whenever you're doing this, because we're dealing with degrees as my angles, make sure that if you're typing things into your calculator, you're using the degree mode of your calculator. If you're in radian mode, you'll be thrown off. So that's how to solve a triangle if I'm given two angles and a side length. Here's another example where we're given two angles and a side length. This one is a little bit different because I'm not immediately given one of the ratios in the law of sines. But if you want, go ahead and push pause on this video and try this on your own. And in just a couple of seconds, I will show you how this one is done. All right, here we go. Since I'm given two angles, the first thing I'm going to do is use the fact that the angles add up to 180 degrees, and therefore 42 plus 68 plus the angle gamma is equal to 180 degrees. That means that gamma is equal to 70 degrees, and once I know gamma is 70 degrees, then I do have a ratio in my law of sines. So I'm going to use my law of sines to find the B, and then I'm going to use the law of sines to find the A. So I have the ratio of sine of gamma over C. So I'll use that in finding the B here. Sine of beta divided by B is equal to sine of gamma divided by C. In this case, that's sine of 68 divided by B, I don't know B, so leave that as a variable, is equal to sine of 70 divided by 28.7. Once again, we would cross multiply and then divide. In this case, we'd cross multiply. I'd get 28.7 times sine of 68 is equal to b times sine of 70. And then dividing both sides by sine of 70 would give me a b value of 28.7 times the sine of 68 divided by the sine of 70. That's the exact value. The approximate value of b there would be 28.32. That's when I plug this into my calculator. So now I know that b is about 28.32. And now we can move on to find a. Once again, you could use the ratio of sine beta over b, but since b is a rounded value, I'd prefer to use the sine gamma over c ratio in order to find the a. So in other words, I know this ratio now, but since we have a rounded value for b, I'm not going to use it. I'd prefer the non-rounded values. So we'll use sine of alpha over a. That is sine of 42 divided by my unknown of a is equal to sine of 70 divided by c. And I know c is 28.7. So that means the value of a is equal to, again, cross multiply and divide, 28.7 times the sine of 42 divided by the sine of 70. That value is approximately 20.44. So we get an A value of 20.44. And then we're done. We've solved the triangle. We have all three angles and all three side lengths. I do want to point out something about this triangle just as a intuitive thing. Notice that beta and gamma were angles that were very close to each other. We had one angle at 68 degrees and the other at 70 degrees. And that meant the side lengths opposite those angles were also going to be really close to each other. 70 degrees was just a little bit above 68 degrees. Therefore, C is just a little bit above B, excuse me. And since the beta was bigger than alpha, we knew that the A value was also going to be smaller than the B value. So since alpha is smaller than beta, A was going to be smaller than B. Let's do another example using the law of sines, and then we'll confirm this example with other tools as well. So let's take a triangle whose side length A is 18, alpha is 30 degrees, and gamma is 90 degrees. Since gamma is 90 degrees, we're dealing with a right triangle. So we're solving a right triangle using the law of sines and the tools that we just looked at. If you want to do this on your own using the law of sines, you can push pause on the video. In a couple of seconds, I will show you how this is done. All right, let's do this using the law of sines. So again, we're given two angles. So the first thing I do is find that third angle. In this case, the third angle is the beta. And doing basic arithmetic, gives you that beta is equal to 60 degrees. So this is a 30, 60, 90 right triangle. Now we can utilize the law of sines. Since I have the ratio sine alpha over A because I know the alpha and I know the A, then I'll use that to find the B and I'll use that to find the C. So I'll use this ratio here to find B, and then I will end up using this ratio to find C. So let's find B using the information we're given. So sine of alpha is sine of 30 divided by A, which is 18, is equal to sine of beta, which is 60, divided by B, which I don't know yet. I can do the arithmetic by cross multiplying and dividing. B is going to be 18 times the sine of 60 degrees divided by the sine of 30 degrees. By the way, we actually know the sine of 60 and the sine of 30 degrees because we've examined the unit circle. If you haven't examined the unit circle, not a big deal here. But sine of 60 is root 3 over 2. Sine of 30 is 1/2. So when you do the calculations, you actually get 18 times the square root of 3 as your value of B. If you wanted to do an approximate value rounded to a couple of decimal places, it's about 31.18. But 60 and 30 are nice angles on a right triangle. So 18 root 3, or I'm just going to write 31.18 for simplified purposes. Then we move on to the next ratio. Again, if you wanted to use beta and B, you could have done that. I'm going to use alpha and A. So sine of alpha is sine of 30 divided by A, which is 18, is equal to sine of gamma, which is sine of 90, over C. And that gives me C is equal to, once I solve this, cross multiply and divide, 18 times the sine of 90 divided by the sine of 30. Again, if you wanted to do this by hand, you could if you knew the sine of 90. Sine of 90, by the way, is 1. And the sine of 30 is 1/2. So we're getting 18 times 1 divided by a half, which gives me 36. So the value of C is exactly 36. So that's how we could have solved this triangle using the law of sines. Now, I want to point out that this was not our only option of how to solve this triangle. Since this triangle was a right triangle, we actually could have used the same fact about finding beta, the fact that the angles add up to 180 degrees, we'd get beta is equal to 60 degrees. And then we could have actually utilized the mnemonic SOHCAHTOA on this one. And if you remember what SOHCAHTOA says, it says that the sine of an angle, like for instance, the sine of angle alpha, this is in a right triangle, is equal to the side opposite divided by the hypotenuse. So the opposite over hypotenuse. In my case, if I'm using alpha, I would take the sine of 30 degrees is equal to the side opposite that. That's, by the way, A in our case, because A is opposite of alpha, divided by the hypotenuse of C. Since I know that A is 18, I could have found C utilizing this. Multiply both sides by C and then divide by sine of 30. That would give you C is equal to 18 divided by the sine of 30, which in fact is 36. So I could have found the fact that C is 36 using SOHCAHTOA if I wanted to. And I could also have found the value for B using SOHCAHTOA. Now that I know the A and the C, I can either use the cosine part of SOHCAHTOA or I can use the tangent part of SOHCAHTOA if I want. So let's use the tangent part. I'll use tangent of alpha. Tangent of alpha is equal to the side opposite of alpha divided by the side adjacent to alpha. That is the leg adjacent to alpha. So in my case, we get 30 as alpha. The side opposite is A. The side adjacent is B. The leg opposite is A. The leg adjacent is B to alpha. And so if I put 18 in there, it's easy to see that B is going to be equal to 18 divided by the tangent of 30. And if you take that and type that in on your calculator, then excuse me. So if you take that and type that in on your calculator, you actually get the exact value. If you do exact value, is 18 times the square root of 3, or the approximate value of 31.18, just like we had before. By the way, that last step, there was another way to find B as well, not using SOHCAHTOA. Once I have the A and the C, I could have also found B using the Pythagorean theorem. And we would get 18 squared plus B squared is equal to 36 squared, since I already know A and C. And so B squared would equal to 36 squared minus 18 squared, and then take the square root of that number. So B would be equal to the square root of 972, which again is exact value of 18 root 3. The approximate value is 31.18. So that's another way we could have gotten B once we knew A and C. But SOHCAHTOA and the Pythagorean theorem led to the exact same conclusion that we got with the law of sines. Again, that only works with right triangles. If I tried that with examples 1 and 2, if I tried to use SOHCAHTOA and Pythagorean theorem, they would not work for the first and second examples that we went over. So SOHCAHTOA only works in right triangles, but as we see, law of sines work in any triangle that we want. So that means anytime we have two angles and one side length of any triangle, then we can solve the triangle with the tools that we're talking about. The fact that the angles of the triangle add up to 180, utilizing calculations with trig functions and their inverses, and using law of sines. That's regardless of whether the triangle is a right triangle, whether it was acute, like this example. This example was an acute triangle because all angles were less than 90. Or whether we had an obtuse triangle. This one was obtuse because one of the angles was greater than 90. So no matter what shape of triangle we have, if we have two angles and one side length, then we can utilize these three tools to solve the triangle. Now, what if we have three other pieces of information? What if we have two sides? In other words, two side lengths and one angle. Well, it turns out sometimes when we have two sides and one angle, we can utilize the three tools that we have here to solve the triangle. However, it must be the case that if we're trying to use law of sines, one of the angles must pair with one of the given sides. So I'm going to have alpha and A, or I'm going to have beta and B, or I'm going to have gamma and C if I want to utilize law of sines with two sides and one angle. Let's do an example to make this more clear. Let's solve the following triangle. A is 38.2, B is 24.25, and alpha is 105 degrees. Let's try to come up with the other side, which is C, and the other two angles, which is beta and gamma. So like I said, this one has potential because we have the alpha and the A. So that means that when I'm using my law of sines, I have this ratio, this left-hand ratio. Also, I have one of the components of the sine beta over B ratio. I have none of the components of sine gamma over C. I do not have the angle or the side length there. So what I can do is I can use this part of my law of sines to find potential values for beta. So we're going to take sine of 105 degrees divided by 38.2 and set that equal to sine of beta divided by 24.25. And that's what we have. Now I can utilize this to find beta, or at least potential values of beta. I would cross multiply. Well, in fact, let's just multiply both sides by 24.25. If you do that, we get that the sine of beta has to be equal to 24.25 times the sine of 105 divided by 38.2. Which, by the way, if you calculate 24.25 times the sine of 105 divided by 38.2, you end up with about 0.61. 31858 976. And it would keep going from there. So something of that value. Now, what we're going to do is we're going to find beta using this equation and sine inverse, the sine inverse function. There is one little catch though. There's actually two values of beta between 0 and 180 degrees that have this output of sine. Now, this is not a perfect representation by any means, but this kind of shows you the picture on the unit circle of why we're getting two angles with that sine of beta being about 0.61. If my beta were this blue angle here, D here is the 0.10. If my angle beta were the blue, then we'd hit this point on the unit circle whose sine value, that's the y value on the unit circle, is about 0.613. However, if I go to this angle, the green angle, we also have the same y value roughly, it's not perfect, but of about 0.613. So both of these angles are going to be legitimate angles where if I plug sine of that angle, I get about 0.613. My inverse sine function on my calculator is just going to give me the one in the first quadrant. What I need to do is I need to realize that the one in the second quadrant is going to be supplementary to the one in the first quadrant. In other words, they're going to add up to 180 degrees, or they'd add up to pi radians if we were using radians. So we can find the green one by taking 180 minus this blue one. So we're going to have two options for beta. The first option is what we get when we take the sine inverse. I'm going to, in my calculator, put the exact value in. By exact value, I don't mean the rounded value. I mean, I'm going to use second and then my answer. Don't round this to 0.61. That might throw you off. Do sine inverse of this value here, whatever it happens to be. But for shorthand, I'm going to type in sine inverse 0.61318.5. I'm just going to put ... making sure we get the exact value. And what that would give me is a beta of approximately 37.82. The other beta, the other option of beta, would be 180 degrees minus the inverse sine of that value. And if you do that calculation, you end up with 142.18 roughly. And you can check that if you plug in sine of 37.82, you get about that number. Again, this was rounded. And if you plug in sine of 142.18, you also get about that number. Now, this tells us one of two things. It either is telling us that both of these options work or that one of these options don't work. In my case, it turns out that this second option does not work. because if you think about the angles of a triangle, if I were to put 142.18 as one of the angles of a triangle, along with angle of 105, those two already add up to more than 180. Therefore, that 142.18 is not going to work as a legitimate angle. So 142.18 does not work. So we only have one option for beta that actually works. I'll cross out the one that does not work here. All right. So now we know that beta is 37.82. Now I'm going to have to find gamma and C. And in order to find one of these, the easier one to find is the gamma. Now that I have two angles, use the fact that the three angles of a triangle add up to 180 degrees in order to find that gamma. So in this case, we would say 105, that's alpha, plus 37.82, that's beta, plus the gamma is equal to 180 degrees. When I subtract 105 from both sides and then subtract 37.82 from both sides, I get a value for gamma of 37.18. That's pretty close to what beta is. So 37.18 degrees for gamma. And now I can use law of sines to find C because I have a ratio for beta and B, I have a ratio for alpha and A, and therefore, since I know gamma, I can set that equal, one of those equal to the ratio for gamma and C. Once again, I like to use the answers that were given that have not been rounded. Since 37.82 degrees is a rounded value, I'll use the sign of alpha over A. So here we go, alpha over A, sine of alpha over A is going to be sine of 105. Let me write that again. Sine of 105 divided by the A of 38.2 is equal to the sine of 37.18 divided by the unknown of C. And to solve this, we'd say C is equal to 38.2 times the sine of 37.18 degrees, all divided by the sine of 105 degrees. That's approximately 23.90 when I calculate it using my calculator. And so therefore, we have solved this triangle. We've found all three angles and we found all three side lengths. That took me understanding that there's going to be two beta values. In this case, one of them did not work. And then utilizing the inverse sine, utilizing the law of sines. Let's look at another scenario. Let's try to solve this triangle. If you want to try it on your own, push pause on the video. I'm going to jump right into it. We're given that we have side lengths of B of 14.5, of C of 12.95 and gamma of 36 degrees. So just like last time, we are given one ratio in the law of sines, or the values in the one ratio of the law of sines, and then one value in another ratio of the law of sines. In this case, it's gamma and C that I'm given, and then I'm given B. So I would use that equality in the law of sines. And when we do that, beta is the unknown. B I know is 14.5. Gamma is 36 degrees. And C is 12.95. So in order to solve for sine of beta, all I have to do is multiply both sides by 14.5. So 14.5 times the sine of 36 divided by 12.95. I could get an approximate value if I wanted. Maybe that's more confusing than it needs to be. But that's what it is. Okay, let's actually write down that approximate value. The approximate value is equal to 0.6581-ish. It goes on beyond there, but just so we have a reference. Now, just like the previous one, there's going to be two angles between 0 and 180 degrees that give me sine of that angle is 0.6581. One of those angles we can find by just taking the sine inverse on our calculator. Again, when I'm typing this into my calculator, I don't use a rounded version as my input. I always use the exact version as my input. That's why I'm putting the dots there. And when I do a sine inverse in this situation, I end up with an angle which is 41.16 degrees. Just like in the last example, the other angle that has sine of that angle being 0.6581 is the supplementary angle, which I can find by just taking 180 minus that 41.61 or 0.16, excuse me, degrees, or 180 minus this sine inverse, if you'd rather write it that way. And that angle is 138.84. Now I want you to notice that this gave us two angles, and both of them are going to be such that when you add gamma, they'll still be under 180. 138.84 plus 36 is still under 180. That means that this information actually leads us to two different options for triangles. So we're going to have two options for triangles. One whose beta value is 41.16 degrees, and the other whose beta value is 138.84. Then we're going to have to find the alpha and the A in both of these cases. Let's just go ahead and do that in the first case. In the first case, we'd have alpha plus 41.16 plus 36 is equal to 180. When I solve for alpha by subtracting 41.16 and subtracting 36, in that case, I get 102.84 as my value for alpha. In the other triangle, we would have alpha plus 138.84 plus 36 is equal to 180. And in that case, alpha would be 5.16. So 5.16 degrees. This gives us, again, two options for these angles. And now that we have alpha in each case, then I can use the law of sines to find the A in each case. Now I'm going to use the law of sines with gamma and C because those were exact values. The beta, remember, was a rounded answer in both of these cases. So let's do case by case. Case one, I would have this ratio, and it would be sine of 102.84 divided by A is equal to sine of 36 divided by 12.95. That means A would be equal to 12.95 times the sine of 102.84 divided by the sine of 36. And in that case, we get an approximate answer of 21.48. So 21.48 is the measurement of A in the first triangle case. We do the exact same calculations in the second triangle case, but instead of having 102.84, we'd have 5.16 as my alpha. So we do the exact same calculation, exact same technique, but with a different angle alpha. And if I do that, then I get an approximate value of 1.98 for A. So this scenario gave me two legitimate options that could work for the triangle. This triangle would have had gamma of 36, C of 12.95, and B of 14.5. This other triangle would have also had gamma of 36, C of 12.95, and B of 14.5. So I get two options in this case. One using the beta that I get with sine inverse, the other using the supplementary angle for beta. By the way, one reason to see that we have two actual triangles that work is drawing a picture. So what we have is the length of C being 12.95. That's opposite angle gamma. The length of B being 14.5. That's opposite of beta. And then this angle here will be my alpha. Well, if I have a length of 12.95, what I can think of is I can think of like rotating this until it makes a triangle. So I don't know the length of A yet. We'll draw it as an infinite length right now. And what you'll see is that if you rotate this down, we get one triangle that looks like this. That's where it touches that other side. And then if I rotate it around and up, this creates a second triangle with the same gamma. 14.5 is the B and 12.95 is the C. So this created two triangles, one where the alpha was really small and the beta was bigger, and the other where the beta was smaller and the alpha was bigger. Those two triangles. And this will happen anytime we can have this scenario. Again, I'm just rotating that 12.95 around in a circular motion, and it intersects that side in two different spots. And so that's going to yield two different triangles. So some problems where we're given two sides and an angle will give me out two different options for my triangle. And the two different options will come when I'm finding my angle using law of sines, and I get one obtuse and one acute option, which those two angles will be supplementary. They'll add to 180. This can only happen when I'm given two sides and an angle. If I'm given two angles and a side, this won't happen. By the way, as we saw in our first example with side-side angle, sometimes a supplementary angle doesn't work because we add to over 180 with the supplementary angle. So sometimes one of them doesn't work. So go ahead and try example 6 here. This is given two sides and an angle, and the angle that we're given is associated with one of the sides given. So alpha and A. Try to solve this one and see if you get two options for triangles or if you get one option. And then if you have two options, what are the two triangles? If you have one option, what is that one triangle? Try this on your own. In a couple of seconds, I will show you how it's done. All right, hopefully you had a chance to do that. If you didn't, you can push pause. I'm going to start up right now. Since we have alpha and A, I'm going to use sine alpha over A as the ratio in the law of sines. And the other ratio that I'm going to use is sine gamma over C because I know the value of C. So going to use setting those two ratios equal. We'll get sine of 45 over 34.9 is equal to sine of gamma, which I don't know, over 28.5. So that means that the sine of gamma has to be equal to 28.5 times the sine of 45. divided by 34.9. That can be calculated using a calculator. Just type it in to the trig functions. That's approximately 0.5774. It goes on from there. We know that there are two angles between 0 and 180 where sine of that angle is 0.5774. One of the angles is just the inverse sine of that 0.5774 number. Again, I'm going to use exact values when I do this, when I type it in to my calculator. Inverse sine of the exact value gives me 35.27 roughly. The other is the supplementary angle, 180 minus the sine inverse of that 0.5774 number. Again, we're using exact angles here. That is 144.73 approximately. You can check that when you plug in sine of 35.27, you get this value. And when you plug in sine of 144.73, you also get that value. So both of these work for this equation. But in this case, if alpha was 45 degrees and I went to try to find beta, we'd take 45 degrees plus beta plus 144.73 and set that equal to 180, right? If I use this second option. But 180 minus 45 minus 144.73 is a negative beta. In other words, negative 9.73. So beta would not be an actual angle of a triangle. These two, the 45 and 144.73, already add up to over 180. So this is an option that doesn't work. So we'll scratch that option there. So that option doesn't work. We're only going to have one option for my gamma that works, and that is the 35.27 degrees. Now that I know that, now I can solve this single triangle by using the tools that we already know. So what we have is 45 degrees plus beta plus my gamma, which is 35.27, has to be equal to 180 degrees. That means the beta value in this case has to be 99.73. So 99.73 is the only beta value that works. Now that I know beta, I can use it to find B using the law of sines. I am going to use the alpha and the A with the beta and the B ratios because remember gamma was a rounded value for the degrees. So sine of 45 degrees divided by 34.9 will be equal to sine of 99.73 divided by my unknown value of B. doing the equation, B would be equal to 34.9 times the sine of 99.73 divided by the sine of 45. Which is about 48.65. So we get a value of B, which is 48.65. We actually expected, well, I should have expected the value of B to be bigger than A and C because the angle beta is larger than alpha and gamma individually. So there we go. So larger angles are associated with the longer sides. So sometimes we get multiple triangles, sometimes we don't, on this side-side angle scenario where we have one angle associated with the associated opposite side. Now, I want to state another thing. Some numerical values don't work for a triangle. There are some values that when you plug them into the equation, they just don't create an actual triangle. So we can't willy-nilly just throw in different values for A and different values for B and different values for C and expect to have a triangle and expect to have a triangle which exists. Okay. Let me give you one example of that. Let's say I wanted to solve the following triangle and somebody told you that the side length of A is 203.8, alpha is 98 degrees, and C is 302.7. Well, it turns out that what will happen is that a triangle with these properties cannot exist. I'll show that using the algebra, and then I'll talk about the intuitive way we should have figured that out as well. All right, so if we try to do the algebraic way, basically we'd use the ratio of sine of alpha over A. We'd set that equal to gamma, sine gamma over C. That's because we have the alpha as 98, the A is 203.8, and we're given the C value, which is 302.7. Now, if we go ahead and try to solve this, we'd end up with sine of gamma is equal to 302.7 times the sine of 98 degrees divided by 203.8. Now, everything looks pretty normal up to this point. Looks just like what we did earlier. But when I calculate this, this is saying that the sine of gamma is about 1.4708. That is a problem for us because sine of an angle is always going to turn up to be between -1 and +1. So if I tried to find the gamma by doing a sine inverse of 1.4708, that would not exist. So there is no gamma that I could possibly dream of which has a sine value that's bigger than 1. And therefore, algebraically, this triangle does not exist. There's no triangle with angle alpha being 98 degrees, side A being 203.8, and side C being 302.7. So there are some things that are just algebraically impossible. Now, for this example, we probably could have figured this out intuitively as well. Notice that alpha is 98 degrees. That means alpha is an obtuse angle. The side length opposite of alpha is 203.8, but that is not the biggest side length. Since C is a bigger side length, that means that using the law of sines, gamma would have had to have been a bigger angle than alpha. Since C is bigger than A, gamma would have had to have been bigger than alpha, but that would have forced gamma to be also obtuse. It'd be more than 98. And if gamma and alpha are both more than 90, then we're already above 180 degrees for our angles of a triangle. So that would be the intuitive way to see that, yeah, we can't have two angles that are above 90. So since we can't have two angles above 90, this triangle does not exist. But you'll see that if you try to solve it algebraically as well. There are other scenarios in which this wouldn't work as well. For instance, if we had angle gamma, I didn't put it in the right spot, but if we had a base length of 25, we had our angle gamma fixed, like in our previous problem. Well, there are scenarios in which this, no matter how I rotate, I can't actually touch the other side. So there are other scenarios that also give us non-triangle shapes as well. So other scenarios where the numerical values given don't align with any triangle. Now, the last thing I want to say is that so far, every problem that we've done, which created a triangle, we used three tools. The fact that the angles of a triangle add up to 180 degrees, our trig functions and their inverses, and then the law of sines. The law of sines is a great tool to solve triangles, but there are a couple of scenarios in which we need another tool. And just as an example of why we would need another tool, let's look at example 8. Let's say I know two side lengths and the measure of an angle, but the angle that I know the measure of, I don't know the side opposite of that. Now, this will create a triangle. I'll just tell you that. This will create a triangle, but the law of sines won't be effective as a first step of solving this triangle. So I can't use the fact that the three angles add up to 180 degrees because I don't know two of the angles. And I can't use law of sines to solve because I'm never given a full ratio. I have the sine of alpha, but I don't have A. I don't have beta, but I do have B. I don't have gamma, but I do have C. So I'm given one component in each of these ratios, and therefore I can never solve because I'm never given two components in a ratio. So I can't use my law of sines tool. I can't use the fact that the angles add up to 180 degrees. I don't have any other reference point right now, and therefore I'm stuck if I just have the tool of law of sines and angles adding up to 180 degrees and inverse trig functions and trig function calculations. You'll also notice that if somebody told you that A was 31, let's say, and we didn't have the alpha, we'd also have one component of each of the ratios in the law of sines. So when do we need that other tool? Well, we need it when we have one component of each ratio and we only have one angle at most. We could have zero angles. But if we had two angles, we could use the fact that the angles add up to 180 degrees to get the third. So we need either one component of each, and then two of those components are sides, or all three sides. And the law of sines isn't going to be enough to solve the triangle. So if we have two sides and an angle in the third ratio, or if we have three sides, then we'll have to develop another tool. And lucky for us, there is another tool called the law of cosines, and that will be covered in a subsequent video. And I will link that video in the description of this video.